Hi, this is Stu Schwartz from MasterMathMentor.com. This is Super Free Response Practice BC question number 3. Super free response questions are similar to the typical free response questions in past AP exams. But instead of having the usual 3 or 4 subparts, these will have a great many more. It allows us to use the problem setup as a source of many inquiries that can be taken and allows us to do an in-depth study of the situation. Because of that, many calculus concepts are tested and some reiterated. Doing these will take more than the usual 15 minutes, but by tackling all subparts, you will know what topics you need to emphasize as you prepare for the AP exam. It is recommended that you go to the MasterMathMentor website and download the PDF with the actual problem and subparts. If you don't have a printer available, use a piece of paper for parts A, B, C, etc. This video will just show you the solutions, although you can fast forward at times to bypass the solutions and just show the problems. Question 3 reads, according to the American Cancer Society, the size of a tumor is based on its length at its widest point. A T1 tumor is 2 centimeters or less. A T2 tumor is more than 2 centimeters but less than 5 centimeters. And a T3 is 5 centimeters or greater. Dr. Finucci, an oncologist, who is a doctor who treats cancer, assesses the tumor's features, and based on that assessment and numerous factors of the patient, he recommends a treatment plan and tries to determine how the tumor will grow or shrink over time. There are many factors involved, but he classifies them based on the following differential equations, where W is the tumor's width measured in centimeters, T is the time measured in months, and K, capital M, and small m are constants. A type A is dW dt equals KW. A type B is in the form dW dt is equal to K times the quantity M minus W. A type C is dW dt is equal to K times the quantity M minus W raised to the nth power. And a type D is dW dt equals K times the quantity W minus small m times the quantity capital M minus W. It should be noted that these types are fictional and created just for this problem. While the American Cancer Society uses the T1, T2, and T3 classifications for the size, to my knowledge, they do not classify them using these differential equations. This problem is all about growth and decay. In BC calculus, there are 3 types of growth decay situations that you should know. The first is simple. It is constant growth. The rate of change of population is constant. This is a differential equation in the form of dP dt is equal to K, and therefore P of t can be written as kt plus c, a line. If k is greater than 0, we have linear growth, as shown in blue, and the limit of P of t as t approaches infinity is infinity. If k is less than 0, then we have linear decay as shown in red, and the limit of P of t as t approaches infinity is negative infinity. If P cannot be negative, like a population of people, then the limit as t approaches infinity of P of t in a decay situation would be 0. We are not much interested in constant growth. We are usually interested in exponential growth. In AB calculus, you learned all about exponential growth. In that situation, the rate of change of population is proportional to itself, meaning that the more you have, the faster it will grow, or the less you have, the slower it will decay. The differential equation for that was dp dt equals kt, leading to p of t is equal to ce to the kt, and this should be memorized. If k was greater than 0, we have exponential growth, and the limit of p of t as t approaches infinity is infinity. If k is less than 0, we have exponential decay, and the limit as t approaches infinity of p of t is equal to 0. Our third growth situation is based upon the rate of change of population being proportional to itself and the room to grow. This is in the form of dp dt is equal to k p times m minus p. And this is called logistic growth. We are interested usually in logistic growth where k is a positive number. And this gives logistic growth where the limit of p of t as t approaches infinity is equal to m. The graph of the curve is a distinctive S-shaped curve that is beginning concave up and then concave down. And the curve will have an asymptote at the carrying capacity, which is the maximum value of m. And as the curve approaches m, it becomes more and more horizontal. Students are not responsible for the solution to the logistic growth differential equation, just to recognize it based upon the DEQ and the shape of the graph. In this problem, we will investigate other types of growth or decay using differential equations not in one of these forms. We will rely on our ability to solve those differential equations and to get a sense of what the graph looks like by examining the first derivative and the second derivative. Part A reads, Jose is told that his T3 tumor is changing proportional to its current size with the constant of proportionality k equals negative 0.2. If W sub 0 is equal to 6, determine the tumor type and then solve the differential equation that describes the size of the tumor. Write a statement that Jose can understand which describes what he can expect about the tumor's size in the long run, and explain mathematically why this is true. This is a type A situation, as the size of the tumor changing proportional to its current size puts it in that category, and dW dt equals negative 0.2 W. Students should know the solution to this, but we will go through the procedure. dW over W is equal to negative 0.2 dt, and then we integrate both sides, getting the natural log of the absolute value of W is equal to negative 0.2 t plus c, and W is equal to c e to the negative 0.2 t. We know that when t equals 0, W equals 6, so the solution to the differential equation is W is equal to 6e to the negative 0.2 t. Although a graph of the slope field of the DEQ and the solution to the DEQ is not necessary, it might help in the explanation. The tumor will always shrink because dw dt is less than 0. And also the tumor will get infinitely small because the limit as t approaches infinity of 6e to the negative 0.2t is equal to 0. This is a 5-point problem. 1 point for setting up the DEQ, 1 point for the general solution, 1 point for the specific solution, 1 point for the statement to Jose, and 1 point for its justification. As a follow-up to that question, Jose would like to know how long Dr. Finucci believes it will take before the tumor is less than 2 centimeters in size, and we would like to determine this mathematically. We set our size equation 6e to the negative 0.2t equal to 2. Since we are not permitted to use a calculator on this problem, we will solve it algebraically. We get e to the negative 0.2t is equal to 1/3. Taking the natural log of both sides, we get negative 0.2t is equal to the natural log of 1/3, which is the natural log of 0 minus the natural log of 3. And therefore t is equal to the natural log of 3 over 0.2, or 5 natural log of 3 measured in months. 2 points for this problem, 1 point for the equation, and then 1 point for the answer with the correct units. Part C reads, Allison has had her T3 tumor assessed as a type B with M equals 4, K equals 0.5, and W equals 10 at T equals 0. Write an equation for the line tangent to the graph of W at t equals 0. Use this equation to approximate the size of the tumor at t equals 2 months. Our equation for a type B will be dw dt is equal to 0.5 times quantity 4 minus W. At the point 010, dw dt, which is the slope of our line, will be 0.5 times 4 minus 10, which is negative 3. So therefore the line will be W minus 10 is equal to negative 3t, or W equals 10 minus 3t. And at t equals 2, W of 2 is equal to 10 minus 6, which is 4 centimeters. 3 points for this part. 1 point for dw dt at t equals 0, 1 point for the equation of the line, and then 1 point for W of 2. Part D reads, use the second derivative of W with respect to t to determine whether your answer in Part A is an under or over approximation of the tumor's predicted size. The second derivative of W with respect to t will be the derivative of the first derivative, which is 0.5 times negative 1, and then by the chain rule multiplied by dw dt. This is negative 0.5 times 0.5 times 4 minus W, or negative 0.25 quantity 4 minus W. So the second derivative of W with respect to t at t is equal to 10, which is negative 0.25 times negative 6, which is 3. This means that the graph of W is concave up at t equals 0, meaning that Part A answer is an under approximation. Our graph shows a verification. We see in red the slope field for the differential equation, the specific solution in green, and the tangent line in blue. And it is obvious that at t is equal to 2, the predicted value of 4 is way under the expected value, which is closer to 6. 2 points for this problem. 1 point for finding the second derivative of W with respect to t, and then 1 point for the answer with a reason. E reads, Donald has had his T2 tumor assessed as a type B with M equals 4, K equals 0.5, and W is equal to 2 at T equals 0. Solve the differential equation that describes the size of this tumor. The differential equation for a type B is dW dt equals 0.5 times the quantity 4 minus W. This is neither linear, nor exponential, nor logistic, the types that students should know the solutions to. So we will have to solve it. We get dW over W minus 4 is equal to negative 0.5 dt. Note that we change the order of 4 minus W and write it as W minus 4 and put a negative sign on the right side because it is easier to integrate. This gives us the natural log of the absolute value of W minus 4 is equal to negative 0.5 t plus c, or W minus 4 equals c e to the negative 0.5 t. And when t equals 0, W equals 2, meaning that c is equal to negative 2. So our solution is W is equal to 4 minus 2e to the negative 0.5 t. Although not required, we see a graph of the equation. 2e to the negative 0.5 t is a decay curve with an asymptote on the x-axis. So W equals 4 minus 2e to the negative 0.5 t will be a growth curve with an asymptote at W is equal to 4. 3 points for this equation, 1 point for the separation of variables, 1 point for the constant, and then 1 point for the actual equation. F reads, if you were Dr. Finucci, what would you tell Donald is the long-range prognosis about the growth and size of the tumor, and explain how you reached that conclusion. Since the limit as t approaches infinity of 4 minus 2e to the negative 0.5 t is equal to 4, and dW dt is going to be a positive number as long as W is less than 4, the tumor will always grow but never get larger than 4 centimeters. 2 points for grading, 1 point for the limit statement, and 1 point for explaining that there is constant growth. G reads, Molly has a type C T3 cancer with K equals negative 1, M equals 5, and N equals 2/3. Based on dW dt, what will be the doctor's preliminary prognosis about the size and spread of the tumor? It seems like a lot is asked, but in reality, this is easy. The form of the differential equation is dW dt equals negative quantity 5 minus W to the 2/3. And since it is a T3 cancer, W sub 0 is greater than 5. That means that except when W is equal to 5, dW dt will always be less than 0, which means that the tumor will always be shrinking. Only 1 point here for the interpretation. Part H reads, find the second derivative of W with respect to t, and based on your answer from Part G, make a sketch of the general shape of the graph of W on the supplied axes. What should the doctor say to Molly? We start with dW dt equals negative quantity 5 minus W to the 2/3. So the second derivative of W with respect to t will equal negative 2/3 times 5 minus W to the negative 1/3 times negative 1 times dW dt. This becomes negative 2 over 3 5 minus W to the 1/3 power times negative 1 times negative 5 minus W to the 2/3. Working with all the signs, we get negative 2/3, 5 minus w to the 1/3 power. So, the second derivative of w with respect to t is positive if w is greater than 5, and negative if w is less than 5, meaning that there is an inflection point at when w is equal to 5. The curve is concave up and then switches to concave down, as we can see in the picture. And that means that the tumor should eventually disappear. We don't know any concept of how long this will take. We would need to solve the DEQ to determine that, but we can see its shape. 4 points for this problem. 1 point for finding the second derivative of w with respect to t. 1 point for a decreasing graph showing concavity change when w is equal to 5, and 1 point for the prognosis. Part I reads, Angie had her T1 tumor assessed in another hospital, but her doctor did not use the same assessment system that Dr. Finucci uses. When she transferred to Dr. Finucci, he took the differential equation that was given to her in the other hospital, dw dt equals 0.5 w times the quantity 1 minus w over 5, and determined that it was a type D tumor. Show his analysis and name the type of growth or decay this tumor should show. If this is a type D, we need to have the parentheses in the form of m minus w, so we will multiply the parentheses by 5 and then divide by 5 on the outside. And this gives us dw dt is equal to 0.5 divided by 5 w times 1 minus w over 5 times 5. And that gives 0.1 w times the quantity 5 minus w, and that puts it in the form of a type D, which is a logistic growth formula. 2 points here, 1 for showing the equivalent form and 1 point for the type of growth. Part J reads, assuming that the tumor in Part I acts according to its classification, describe to Angie how the tumor will change over time in a sentence or two. On the axes provided, draw a simple sketch of the projected size of the tumor over time. Since the model is logistic, the tumor is always growing. Its growth will be quick at first, but then will be slower, and the tumor will never be larger than 5 centimeters. We can see the graph, and it models the logistic curve in the S form with a horizontal asymptote at the carrying capacity of 5. 3 points for this problem. 1 for stating that the tumor is always increasing in width. 1 point that talks about the rate of growth, and then 1 point for the actual sketch. Part K reads, how large will the tumor described in Part I be when it reaches its maximum growth rate? And we need to show how we arrive at the answer. Students should know that the tumor will reach its maximum growth when it reaches half its carrying capacity of 5, which makes it at 2.5 inches. However, we're asked to show how we arrive at the answer, so we take a look at the second derivative with respect to t, and that gives us negative 0.1 w plus 0.1 times the quantity 5 minus w times dw dt. We can do some algebra here and write this as 0.1 times the quantity 5 minus 2w times dw dt, and we're going to set that equal to 0. dw dt is never going to equal 0 because the tumor is always growing. So we set 5 minus 2w equal to 0, and getting w is equal to 2.5 centimeters, which is half the carrying capacity. 2 points for this problem, 1 for finding the second derivative of w with respect to t, and 1 point for the answer. The remainder of the parts to this question are based upon this situation. On a particular day, several patients were diagnosed with type D tumors with varying sizes. Its parameters are k equals 0.25, little m equals 2, capital M equals 6. To the right is a slope field of the differential equation describing the tumor's growth. For each subpart, you are given the tumor size when diagnosed, t equals 0. Draw the particular solution onto the given slope field, give a mathematical explanation for your answer, and generate a short prognosis for the patient, paying attention to the projected long-term size of the tumor and growth. Since the number of parts will rely on this formula, it's a good idea to set up the differential equation. dw dt equals 0.25 times w minus 2 times 6 minus w. Part L refers to Jason, whose initial tumor size is w equals 1.5 centimeters. Our initial dw dt will be a negative number, so w will be getting smaller, and following the slope field, the tumor is expected to shrink quickly, and in about 2 months it should dissipate. This will be a 3-point problem. 1 point for generating the graph, 1 point for an explanation, and 1 point for the statement. Part M deals with Derek, whose initial tumor size is 2 centimeters. dw dt is equal to 0, and thus w will never change. The tumor is expected to stay at 2 centimeters wide and never grows or shrinks. Again, 3 points for this problem, 1 point for the graph, 1 point for the explanation, 1 point for the statement. N refers to Helen, who has an initial tumor size of 4.5 centimeters. dw dt is positive, and w will therefore always be larger. But the closer it gets to 6 centimeters, the smaller the rate of increase. So the tumor is expected to grow, but never above 6 centimeters. As before, 3 points. 1 point for the graph, 1 point for the explanation, and 1 point for the statement. In part O, Ray has a tumor whose width is initially 3 centimeters. We would like to use the second derivative of w with respect to t to justify the shape. We first note that dw dt will be positive when w is between 2 and 6. Multiplying out dw dt equals 0.25 times the quantity negative 12 plus 4w minus w squared. And therefore, the second derivative of w with respect to t is 0.25 times the quantity 4 minus 2w dw dt. And since dw dt is positive, in the interval 2 to 6, we are just looking at 4 minus 2w. The graph will therefore be concave up if w is between 2 and 4, as dw dt will be positive, and concave down when w is between 4 and 6, as dw dt will be negative. So, the graph will always be growing, but it grows faster before it reaches 4 centimeters, and then its growth will slow down, and it will never get larger than 6 centimeters, as the limit of dw dt as t approaches infinity will be 0. 4 points for this problem. 1 point for the second derivative of w with respect to t, 1 point for the graph, 1 point for the explanation, and then 1 point for the statement. Part P refers to Laura, whose initial tumor size is 8 centimeters. dw dt is less than 0, and therefore w will always be smaller. But the closer the tumor size gets to 6 centimeters, the smaller the shrinkage. So the tumor is expected to shrink, but never below 6 centimeters. As before, 1 point for the graph, 1 point for the explanation, and 1 point for the statement. Part Q reads, Laura has had some calculus, so she decides to approximate the tumor size after 3 months using Euler's method with an increment of 1 month. Show the procedure and explain why this size increment with Euler's method can lead to a false conclusion. When t equals 0, w is equal to 8, and therefore dw dt is equal to 0.25 times the quantity 8 minus 2 times the quantity 6 minus 8, which is negative 3. dw will be dw dt times delta t, and delta t is 1, so therefore dw is simply equal to dw dt, which is negative 3. So when t is equal to 1, w is equal to 8 minus 3, which is 5. Our dw dt is 0.25 times 5 minus 2 times 6 minus 5, and that is equal to 3/4. And therefore dw is also equal to 3/4. So in month 2, w is equal to 5 plus 3/4, which is 5 3/4. dw dt is 0.25, quantity 5.75 minus 2 times 6 minus 5.75, which is 15/64, making dw 15/64. And now when we move to month 3, we get w is 5 3/4 plus 15/64, and that becomes 5 63/64 centimeters. We saw on the previous slide that dw dt should always be negative, and therefore the tumor should always be shrinking. The problem is that the 1 month increment is too large, leading to an error in Euler's method. 4 points for this problem. 3 points for each successive value of w, and then 1 point for the explanation. There are 46 points available for this question. There is no exact formula for what number of points will constitute a 5, 4, 3, 2, or 1 on the AP exam. However, these percentages are what have been used in the past based upon exams released by the College Board. While you can extrapolate for just this question, realize that this question only tests a limited number of AP topics. So it is recommended that you do a number of the super free response questions in this series. Then combine your results, total your points, and then use these percentages to get a feel for how you will do in the AP exam. And more importantly, what concepts you need to strengthen in order to improve your score.